Welcome to Chem 1A at Shasta College Screencast. This is for Chapter 2, and it's the first screencast dealing with atomic structure. And let's start by considering the building blocks of the substances that make up our world, those things called elements. And the building blocks of the elements are, of course, atoms. Now, you hopefully have previously heard that atoms are in turn made up of even smaller particles called protons, neutrons, and electrons, and we're going to look into that a little bit. Protons have a positive charge, neutrons have a neutral charge, and those two things together make up the nucleus, and that's where almost all of the mass of an atom is. Here's a little chart that shows some of the values. Proton we often symbolize by P, neutron by N, and there is the mass of a single proton in grams, mass of a neutron in grams, and then masses in what are called atomic mass units, more on that in a bit, and the relative charges. And then also here's information for electron, which we'll talk about next. The electrons have a negative charge, they surround the nucleus, and they make up almost all of the volume of an atom. So if this represents the nucleus, we sometimes very simplistically represent the electrons as being in rings or spheres or orbits around the nucleus. This is very simplistic, but it's at least a place to get started. And then the electrons are moving around very quickly, and they essentially occupy this whole sort of spherical space. Just for a little bit of scale, the atom itself is on the order of 10 to the minus 10th meters in diameter. Of course, that's going to vary from atom to atom, but in the ballpark of less than, or about a tenth of a billionth of a meter in diameter. And then the nucleus is about 10 to the minus 15th of a meter in diameter. Again, ballpark varies from atom to atom. Both are very tiny, but to just give you a scale of things, if you could blow an atom up or expand an atom to where the atom occupied the size of, let's say, a big sports arena, then a nucleus, relatively speaking, would be about the size of a pea or a blueberry in the middle of that. And all of the space would be taken up by very tiny electrons moving around rapidly. A little bit mind-blowing. Okay, now let's go through a couple things about atoms and what they're made up of. And we're going to be referring to the periodic table. So here is the periodic table and a representative element, let's say oxygen. And the top number here, the 8 in the case of oxygen, is what's called the atomic number. And the atomic number we sometimes symbolize by the letter Z, and it specifies how many protons as well as how many electrons there are in an atom of that element. So oxygen would have 8 protons in the nucleus and 8 electrons surrounding the nucleus moving around. Simplistically, we could show it as something like this. And important to note, if we're dealing with atoms, the positive charge due to the protons and the negative charge is due to the electrons equal. There's 8 positive charges balanced by 8 negative charges. And if we're dealing with an atom, it's overall neutral. Now there's another number called the mass number. We symbolize that with the letter A. And that gives us the total number of protons and neutrons in a particular type of atom of that element. So if we look at, again, oxygen, the number on the bottom, the 16.00, is not actually the mass number, it's the atomic mass. And we'll try to clarify this distinction. So the atomic mass is 16.00, but it turns out that a typical atom of oxygen, if we round the 16.00 or whatever the number is, in this case we round it off to the nearest integer, then 16 is the mass number of the most likely or most common type of oxygen. So what we're going to do is we'll say an atom of oxygen has 8 protons and 8 electrons. The atomic number is 8. The 16, now in this case, remember, rounded off, indicates that we have a total of 16 protons plus neutrons. Since we know we have 8 protons, 16 minus 8 tells us we have 8 neutrons in that particular sort of most common type of oxygen atom. And how we represent this is we symbolize it by capital O for oxygen, and then we can either go -16, indicating that the mass number of this type of oxygen is 16, or we can write it as O with a superscript 16 on the left and a subscript 8, which is the atomic number, on the bottom left. And since 8 for the atomic number means we're dealing with oxygen, that's kind of redundant, so sometimes we leave that off. So all three of these are ways we can symbolize an atom of this kind of oxygen, this type of oxygen atom. Okay, so let's try this with carbon, and let's describe a typical carbon atom. Hopefully you'd look at the 6, and you'd say that that means it has 6 protons and 6 electrons. You'd look at the 12.01 and say, well, that's pretty close to just 12. So probably the most common type of carbon has a mass number of 12. So we say carbon 12 written this way symbolically or this way symbolically, and 12 total protons and neutrons with 6 protons means there have to be 6 neutrons. And then again, our sort of simplistic way of drawing this might be to represent protons and neutrons in the nucleus and then electrons surrounding it. Okay, so this is the most common type of carbon atom, a typical one, but watch closely, and it turns out that this type of carbon atom exists as well. So back up a sec and look for the difference, and perhaps you notice this nucleus has one more neutron than the previous kind of carbon atom. This is a carbon atom that has a mass number of 13, not 12, and it has 6 protons and 6 electrons like any carbon atom, but it has a total mass or a mass number of 13, which means it has 7 neutrons, and we can write this as carbon 13 or 13 carbon as shown here. And some carbon atoms are like this. So once again, look closely. Notice one more neutron. So now we have 8 neutrons along with the 6 protons and 6 electrons. And this is an atom of what's called carbon 14. Now it turns out in nature, most carbon atoms are carbon 12. There's a few carbon 13s, a few carbon 14s, and in fact there are other what are called isotopes of carbon. And those are atoms of the same element that have different masses because they have different numbers of neutrons. So with our example of carbon, we have carbon 12 with 6 neutrons, we have carbon 13 with 7 neutrons, and we have carbon 14 with 8 neutrons. They're all atoms of carbon, but they differ in their masses because they have different numbers of neutrons. And just as a note, they behave chemically the same way, but their nucleus is a little different, which has some ramifications that we'll get into in more depth much later in the course. Now, there's a thing to note. If you go out in nature and just collect sample of randomly occurring carbon atoms, almost all of them will be carbon 12s and then very small numbers of the others. And the 12.01 that you see on the periodic table is the average mass of the naturally occurring isotopes. So here is a summary of that idea. What's called the atomic mass, or sometimes atomic weight, is the average of the masses of the naturally occurring isotopes of a particular element. And let's do an example of this with chlorine. And we'll use chlorine because it has 2 naturally occurring isotopes, chlorine 35 and chlorine 37. And notice that naturally occurring chlorine is about 3/4 chlorine 35, and atoms of chlorine 35 have a mass of pretty close to 35, 34.969, a little more precisely, in what are called atomic mass units, symbolized AMU. And then the remaining about a quarter of the chlorine is chlorine 37, has a mass of almost 37 AMU, 36.966. And if we take the fractional abundance, the fractional amount of chlorine-35, multiply that by the mass of chlorine-35, and add that to the fractional amount of chlorine-37, about 24%, times the mass of chlorine-37, what we get is this sort of weighted average that is 35.45, rounded off to the right number of significant figures from our data here, AMU. And that is where this number comes from. This is the atomic mass. It's the weighted average mass of naturally occurring, in this case, chlorine. And again, remember, it's made up of some chlorine-35s and some chlorine-37s. And that's going to be true in general, how we have determined atomic masses for different elements on the periodic table. And that's it for screencast number 1 for chapter 2.